Do that. Again, I forget what I did. I don't know if I want to walk. In this measurement. No, it's just a local page, but 5 feet square. Oh, yeah. And show going to the bonus.
Hey guys, hello everybody. I think I will make the first one announcement. So we have, let's see, the syllabus. So we have scheduled transformers for this week, but we still need to finish sec-to-sec models. So I believe all our schedule will be shifted by 1 week. So maybe we will skip APIs or maybe multimodal LLMs, we will see. So we will start transformers next week. But transformers and transfer learning, they are related, so I hope it's fine. Okay, so this is just quick announcement. I graded half of homework, so half of students got the feedback, and they will finish today other homework 1 grading. Okay, so today the plan is to finish language models slides and to start working on the homework 3. And on Wednesday and Friday, we will talk about sec-to-sec model and sec-to-sec with attention model. Okay, so last time we stopped on this notion of entropy, perplexity, which is 2-power entropy. And which we saw that the best value is 1 when the loss function is 0. But let's think about the worst case. So, and the answer is on the slides. The worst case is the size of dictionary. So when we will have the worst case for distribution for entropy, when the distribution is uniform. So if the probability is 1 over size of our dictionary, then we will get 2 power this log the size of our dictionary. But I hope you understand that this metric perplexity actually doesn't reflect the true state of the things, because it's a language, and if our model can guess pretty well the probabilities of the words, but maybe the phrases won't have sense. We will see this later when we will talk about sec-to-sec and translation. So yeah, let's move forward. Okay, I will skip these things because nowadays we're not using these language models. So, and like before transformers, they use the same embeddings for input and before softmax just to reduce the number of parameters. But I think for large language models, because they have billions of parameters, just extra embedding layers that doesn't introduce much more parameters. Okay, so yeah, there are some examples. of training language model on LaTeX texts, then on the code texts, and let's talk a little bit about interpretability. So if you look in your neural network at different nodes, we call this neurons. These neurons can take, for example, if there is hyperbolic tangent activation, they will take values between -1 and 1. If there's sigmoid activation, they will take, or a loop between 0 and 1. So when you pass the phrase in your model, then some neurons will take large values, some neurons will take small values after, after activation function. So if you look at the different neurons, you can find some neurons that will track the end of line, for example. So like red color stands for the higher value of this activation function. Some neurons will track the opening and closing of the quotations. So the neuron will take high values after opening quotes and then take lower values after. So yeah, some neurons will keep track of the opening brackets. So some will take care of if or for statements. What is here? I believe it's also brackets. But some neurons will be activated during the sentiment. And this is was an interesting observation. You can see that for words beautiful, exciting, one neuron has one value, and for roast and like bad sentiments, the neuron takes another value. So what does it mean? It means that neural network learns not only the structure of the data, but it learns something that even we people can't sometimes understand from the text, the sentiment. And this was the turning point for NLP in 2017. And with large language models, it went much further. So this is the Alexander Karpathy broken blog post. So then if we could find such a neuron, then we can just keep this neuron, for example, with value 1, and then generate text. And surprisingly, if we keep this neuron high, then the reviews will be positive. If we keep this neuron low, then the reviews will have negative sentiment. Well, now again, with large language models, it's much easier. You can just ask what you want to generate, but at that time it was an interesting observation. Okay. I think, yeah, that's almost it. The last thing about evaluation of a neural network model, you could create some sentences with different, for example, verb forms like is or are, and check, so generate with your model texts and sorry, generate not the text, but this specific verb and check with the correct form. And if your model provides the correct form, then you will get higher accuracy. If incorrect, lower. Let's see. Um, Also, the same technique is used to evaluate the biasness of the model. Like you've heard about this, AI models are biased. Like you can use, for example, um, male or female after some phrase. Like, and let's see if I have this example here. No, but so, for example, you can create a data set with can you think about such example when the next word, I mean, in other language like Spanish, Italian, they have endings like for female vowels, and for male it's another vowel o, and for male female a. But in English language, maybe like girl or boy. So if model will choose more often boy than or man, then these scientists that write these articles about biasness in the model, they will write this in some, I don't know, science or other popular journals. Oh, these models are biased, but then could you understand how these models work or how they're trained? Maybe not, but at least they know how to evaluate this biases of the model. And of course, it all depends on the data on which they were trained. But this is one of the methods how to evaluate the models. Okay, that's it with our previous week. And now I want to go to homework 3. We will code a convolutional language model, and your homework will be to code recurrent language model. Okay. So week 3. So yeah, today now it's week 4, but homework is still free. And we will use large language models to solve homeworks on large language models class. Like, okay. So first we need to upload the data, and we can use our code from week 3 practice. I believe just this line. Mhm. But we will join uh, together title and So this code is written for you, drawing these lines. Okay, and we will create the character level language model. Before that, we talked about word level, token level, but why don't we use just characters? And then the dictionary will be much smaller. If we use and lowercase and uppercase characters, it still will be about 50 something tokens. So first we will just calculate all the tokens. So it will be set of joining of all lines. Join of all lines. Okay. Okay, and we have just 136 tokens. So this will be the size of our dictionary. Okay, so next line, we should create a dictionary which maps our tokens to indices. If you know other way to do this, it's fine. I will do zip of our tokens and range. It's interesting. I don't know if I can use range here because in my code I used a list of range, but let's see. Maybe it works. In No, it didn't work. So, oh, because we should cast into dictionary first. Let's see, dictionary. Okay, it worked. Yeah, when I wrote the code, I used also I cast range into list, but it works even without additional casting range into list because range is generator and it looks like it's working with zip. So now we have this dictionary token. We can take a look token to ID, for example, of character A. We have some index. Okay, then this code is written for you. We create batches. So do you remember why there are zeros in the end of lines? Yeah, it's padding. So one stands for begin of sentence. Let's see. Yeah, BOS, and zeros will stand for end of sentence. And we pad with end of sentence. Okay, so our language model should predict the next token based on the input sequence. And if we use convolutional model, then it will be similar to n-gram model. depending on which kernel size we choose, so for example, kernel size of 5, then we will look at 5 tokens. In your homework, you will implement recurrent model, and recurrent model can take a look at the entire input sequence and provide the next token. But so this is the idea. Let's write this model. And here I will use just ChatGPT. So just copy paste this function and ask to populate it. So let's see. Instead of writing everything. Yeah, so it created embedding layers, padding, convolution. Now we will just comment this code. So I don't need the second part, I believe, because it was actually provided, but I will use this part from embeddings, I believe. Let's see. Yeah, from super. And instead of forward, we have call, which is actually which performs the same as forward. So, okay, embeddings. There's also parameter window size that it doesn't understand. Let's see. Um, In our case, it's filter size. Okay, so yeah, let's add this parameter in our module in init window size, and then we will add here self window size. Size, and then here we can use self window size. It will be the size of our convolutional kernel. Okay, so it looks good now. So we create embeddings from the number of tokens to the embedding size. Then we add padding, and we use ChatGPT. We use two-dimensional padding, which takes 4 parameters: how to pad from the left, right, up, and down. We pad only from the left. Because if you look at this model, for example, quietly will be our first token, like begin of sentence. And to generate a next word, we don't want to look at the next word. So we will actually pad by zeros from the left. And when we take the convolution, it will look only at the word quietly, and we will predict the next token. Does it make sense? So that's why we pad from the left. Let's see. Let's use the default values, for example, 5 here, window size. Okay. Now the call function. Let's copy paste the forward from ChatGPT. So this is how you should solve your homeworks. Okay. Okay. And now let's look at this code if it's correct. So the input IX is the batch typically. So we apply embedding layer to input batch, so it looks correct. Then, because we use convolution, we change the last parameter dimension stands for the length. So we change such that the last parameter now is the embedding shape. After that, we apply our two-dimensional padding, and oh, sorry. No. I was wrong. So our last dimension is embedding size, and then we make the last dimension as the length of our sentence. And then we apply padding. And after that, we apply convolution. And then we convert back have the last dimension as the length. And finally, we apply fully connected layer. And fully connected layer, let's see, it should go from the embedding size to or hidden size, which is actually the number of, wait a second, hidden size. Let's see, convolution. Yes, convolution will transform our embedding size into hidden size. So a linear layer will transform hidden size to the shape of our dictionary, because you remember we want to predict the probabilities for each token with the number of tokens. Okay, it looks correct. Let's run and see if we pass assertions. Yeah. So next step. One more test. Okay, this is the main part, actually, why I wanted to solve with you this part of the homework, loss function. So first we have some code which computes mask, and what it does by the input batch of sentences, it computes a mask where the last one the last true value stands for the first end of sequence. So for example, here we have 1, 2, 3, 4, 5, the first end of sequence. And here we have 1, 2, 3, 4, 1, 2, 3, 4, 5. So we take our mask such that the last true value corresponds to the first end of sentence. And why do we need this? Because we don't want to predict next token for this end of sentence tokens. So our goal will be now to write the cross entropy loss, which after this position will be multiplied by 0. So we will take care only of the softmax applied to tokens without padding. Does it make sense? Okay. Now let's again ask ChatGPT to write this function, but it's pretty straightforward. So yeah, ChatGPT also says that it will create a mask. Okay, so I will copy this code from, let's see. So we have here the input batch, I believe. Then yeah, and this will be padded batch. Then we apply our model, and what our model does, okay, let me first paste the code and then I will explain. So what our model does, it takes as input this batch of sentences. Then it applies embedding layer, it applies convolution layer, and in the end, it applies fully connected layer that maps our embedding into shape of the entire dictionary. So, and then we apply softmax to this vector, so we get probabilities. And we know the true value. We know which token should be next. So this will be our target. So if we apply one hot encoder to our next token, so it will have one only at one position with index 66, and multiply by this output, then we will get the probability only of this next token. And actually, we want to maximize this probability. So, okay, so we have for every token, we have this output of the model of the size of our dictionary. So it's number of tokens. And also we'll have these outputs for the end of sequence, or end of sentence tokens. So this is the output from our model. Then we have true values, and if you look at the code, the true values are shifted by 1. So we want to get, for example, the probability with index 66 from the first output. We want to get the probability with index 67 from the second output, and so on. And with 0 for this one. So we kind of want to get only these probabilities. And the easiest way is just to multiply this vector by 1/4 encoder of these indexes. Does that make sense? Okay, so I will clear these drawings. And first I will write using 1/4 encoder, but then I will use the code that ChatGPT provided, which is just one line, but it's a little bit harder to understand from the first glance. Okay. So yeah, here's so logits are the probabilities before applying softmax. And we take all except the last element. The reference answers will be shifted by 1. So we take our data, but from the index 1 instead of 0. Okay. Now I will write first my code here. We will create 1/4 encoder for it understands. So torch, no, it's not torch1. There is another function, f functional 1/4 of input ix shifted by 1. So then we should indicate number of classes, the size of 1/4 encoder, which is n tokens. That's correct. That's correct. Okay. So this line creates 1/4 encoding for our targets. Actually, I could use, instead of input ix, I could use here reference answers. Okay. Then I will just multiply the output from my model, the logits, by this 1/4 encoders, and I will get actually only the probabilities of the next true token. So loss loss, we can use loss, I believe, just loss. Okay, loss equals so okay, first let's multiply what is the name? Logits by one-hot encoders. But we should apply softmax to our logits. As you remember, the in cross entropy we have log of p, log of p. So to get log of p, we should first get p probability. So we should take softmax and then log. So we can use torch log softmax of logits, and then multiply by one-hot encoder. And finally, we should sum up this along the size of our dictionary, just to rid of one extra dimension. And okay. I have also mask, but I don't see in my code. So after that, we should also calculate the number of tokens and the number of tokens, because we need to divide by n in our loss function. And the number of tokens we can calculate with a mask. So I will also create a mask. And my mask will be input tokens. Input tokens is our reference answers. Reference answers. Okay, now it understands what I want to write. Not equal to the index of end of sentence. Okay, that's correct. Yeah, I have the same. So it will return once for tokens different from 0. But also, let's see. I should by 1. Um, I think it's correct, but I'm just thinking maybe I should take one more token into consideration or not. Oh no, we don't need, because it says first first EOS also don't count. Okay, now then it's correct. Okay, and finally we should divide by n. So this will be the mask dot sum. And because cross entropy loss is the negative likelihood, we should also use actually negative. I don't know if we need sum. I don't think we need sum, just negative. Return negative loss. So the code that provided ChatGPT is exactly the same. Now let's try to understand. So it uses the built-in functional cross entropy. It takes logits from our output logits. Then it applies reduction none, and reduction none won't sum up. So typically cross entropy also sums, oh, okay, we have formula sums the values. But if we use reduction none, then it won't sum up the values. Oh, it also created mask. Okay, it's exactly the same that I have. And finally, it calculates this loss multiplied by mask, sums and divide. Okay, so now let's just, okay, I will without return. Let's just print these losses and make sure that we have the same results. Print mean loss. And so this is the loss that ChatGPT wrote. And this is our loss. Let's call it loss. Wait a second, loss 1, for example. Loss. Oh, we have some problem. Okay. Let's double check my function. Okay, we apply softmax and I didn't indicate along which dimension. Dimension -1. And let's see if it works now. No, it's still not working. Okay. So torch log softmax times one hot encoder sum. What is the error? The size of tender. Maybe I calculated mask correctly. Second, I will look at my solution. So here is my solution. And it looks the same, but I will just copy. And let's see. Okay, now we have problem with built-in cross entropy. No, it's still with mine. It's weird. Where?
So you see reference answers right there, change it to dot B shape.
Here?
Or keep it in the form, but just change the view to dot B shape.
Mm-hmm. Because it's not a torch.
It still needs to make it.
Oh, but it needs like.
No, that's what.
Oh, wait. Well, anyways, here is the correct solution, and actually I don't know what's the problem. Well, let's just keep our loss from ChatGPT, and hopefully we will pass the assertions. Oh, okay, we should also fix here. Okay, yeah, we should stop, but yeah, you will see the correct answer in the recordings. So we should a little bit adjust ChatGPT output, maybe. Yeah, so we should use tokens to ID EOS instead of EOS IX and so on.
I got the same error as you that first time.
Yeah, because this last token should be actually this.
Yeah, does it work now?
Yes.
Oh.
Yeah, now it works. Because end of EOS like this token wasn't defined.
Was the reference? It was like why I was confused. It was the reference answer just like, okay, I need to reshape. It said it didn't.
Sorry, 1 second, I will stop.